So thanks. Welcome to our talk. I'm Jan, in this talk with Abdel today. And yeah, thanks for coming to our talk. It's a respectable bunch at this time of the day and the last day of the conference, so certainly appreciate it. Today we're going to talk about a blueprint architecture that we're working on at Cloudera to basically come up with an end-to-end life cycle for data. And it's explicitly about a life cycle. This is going to be about IoT, manufacturing in IoT, and what it really means if you want to process this data, if you think about lots of manufacturing plants on a worldwide scale and how to consolidate all this data, and then also do analytics, streaming analytics, and then more even deep learning. So we have a little demo that we're also going to show. Hopefully all goes well on that. We all know how demos go. And so I'm going to jump right into this. I think we'll do like 20-15 minutes of talking and then 15 minutes of demo and the rest for Q&A. So I don't need to talk a lot about this. This is basically just, what's Industry 4.0? It's a buzzword. It's basically about a vertical within a vertical. This is a segment within IoT. It's about how does manufacturing and how do autonomous devices in the field that have been manufactured, how do they impact the market of IT? And I think generally the whole industry agrees that the opportunity is immense. And that's as much as I want to say on this slide. What are typical use cases that we run into with our customers? One of them would be process monitoring, which is basically singular process monitoring that wasn't possible before. It's about hooking up one machine or one machine park in one site. Example would be like cycle time monitoring for CNC machines or other machines like EDM machines. What you want to do is you really want to try to figure out what's going on, which you couldn't do before. You want to do basically reduce downtime. Then there is another thing when you try to consolidate machines that are then enabled for IoT manufacturing sites, then you can consolidate them into a single pane of glass across the world. That is the next step. So one example that we've been working on is, for example, when there was a customer that wanted to basically the pressure that he exerts, the torque that he exerts on when he is screwing together components, and he wanted to basically roll out over a command and control bus to all of the plants the same amount of pressure after he calibrated the pressure or found out which pressure is best. Other things are like saving the in-fab sensor data forever and be able to do forensic analysis on it retrospectively, which is a lot of batch data. And it just reduces the scope of your service campaigns or the warranty costs if you have to do one of those campaigns. You just can run over all of the data and get to root cause analysis much quicker. One thing that we'll be talking about today is sort of recalibrate manufacturing robots, or at least have an approach of how to predict why something is going wrong in your manufacturing pipeline. There's the general quality yield optimization part, right? So the way that we use our platform to do this now, as we've all learned yesterday, is also now incorporates Apache Flink for real-time analytics, but in order to get data, in order to aggregate data, we use other components of our platform, starting with Minify on what we call the edge, of course, IoT gateway, sometimes the sensors and the agents themselves. And then we also have Apache Kafka in our distribution. What the typical setup for that is that you aggregate from those agents very quickly into sort of a local Kafka. So that could be a small Kafka cluster, 4, 3, 5, 10 nodes in a manufacturing plant that then sends data onto an upstream system that is significantly larger in order to consolidate. So this is a typical pattern. So when you see one Apache Kafka on that side, it means there's actually many Apache Kafka boxes. What we also have as part of a distribution is a tool that allows you easy and very consumable routing and curating and cleansing of the data, which is Apache NiFi, which we will show also in our demo, before we then syndicate everything into a central Kafka instance. That is really where all of the, basically all of the processing, the real-time analytics should take place. So that is sort of best practice, because you don't want to duplicate all of that work to 100 sites. This is really where sort of the knowledge transpires. This is where you want to be informed about your real-time results. This is where you want to scale your analytics application, and so that is why you sort of have a big funnel and then syndicate in a central Kafka instance. And most of the people in this room probably know how well Flink works together with Kafka. We're going to be what we try to tackle with this are basically two main challenges. The traditional solutions, on the one hand, are pretty much local and limited. So if you think about doing aggregation and IoT enabling, quote unquote, systems that are in a fabrication plant, right? You often are focused on a single process, right? You do these analytics for each plant. Sometimes you have analytics teams or data teams for each manufacturing plant or each manufacturing product, so to speak, that is located in a certain fab. And what you're really missing out on is the opportunity to catch global trends. If, for example, if two different product lines use the same substrate or base material, and you have a problem with that in the process that you actually measure on, let's say some kind of lubricant or some kind of fluid that you use in your manufacturing process, and you measure it, and you don't connect those two things together, then you are missing out on that. You can't really reconcile what's going on a global scale. There is also a problem with sort of condition-based analysis. Often these edge analytics checks simple IoT sensors, they have basically hard-coded threshold that they go against. And you can't really correlate that against reference data if you have it somewhere. Another thing, obviously, is that if you don't have a simple tool that allows you to come up with this data wrangling in a pretty intuitive way, it ends up being sort of an embedded coding nightmare. So that's one thing, and Abdel will talk about how we sort of try to tackle this column. And the next column is actually how you do this with many, many data sources that have increasing complexity and where volume is just exploding. So this really goes into data from different time universes. If you think about different manufacturing plants, if you think about different machines, they all have their own timestamps. So you need sort of a system if you want to do analytics on them in real time. The time domain needs to be reconciled, right? And then it truly enables you to set up complex event processing use cases in the manufacturing realm, and which otherwise you can't. So the notion of bringing Flink and other CEP frameworks into this is not really well established, and so you need to have this cohesive glue from the IoT world into the large data processing world, pretty much. And then, of course, what you ultimately want to do is you want to be able to deploy more advanced analytics in order to predict that a failure is going to happen in your manufacturing line. Because if you can predict that, then you maybe can take action at the beginning of the manufacturing process, and you can make sure that you don't have another 1,000 items running through your manufacturing line before you actually find out, oh wow, now all of these 1,000 items have an error in them. So that is why actually machine learning models in the manufacturing space, in this Industry 4.0 space, and predicting those errors via machine learning algorithms is very relevant. So with that, I'm going to hand over to Abdel, who's going to talk about how we try to tackle that.
Yeah, thanks. So here we have like two main challenges. The first one is how we can move the data from the edge, from the different plants, from the sensor, into where my Kafka and Flink is. And also, how can I bring other data sources, like enterprise data sources, not only industrial, to be able to do this correlation, because a value of sensor doesn't mean much if it's not related to its contact. So maybe information on when I did my maintenance or how much efficiency I'm getting, how much pieces I'm constructing is important. And this will be tackled with NiFi. The other part, I think most of you already know the part of an answer at least, which is Apache Flink, and also how we can integrate machine learning into this loop to be more efficient and more predictive. Let's start by presenting what's Apache NiFi. So Apache NiFi, it's an open source ETL on steroid. It's like distributed systems that have out-of-the-box connectors to very large number of data sources. We have maybe around 300 processors today. So it can give you the possibility to connect to several data sources like GMS, brokers, Kafka, S3, MongoDB, like large ecosystem, to move this data and store it somewhere. It can be in Kafka, it can be in S3, in HDFS, wherever you want. While you are doing this, you have also the ability to do some transformation, which are really different and complementary to what Flink can do. Here we are talking about ETL, transformation, like you are getting data as CSV from different files from the plants, and you need to put it in Avro for Kafka before Flink application can consume them. So we are talking about this kind of transformation. You have also this NiFi registry that can help you to version your development and build the DevOps chain on top of it. But what's really important here is that this is real distributed system. So you can have your NiFi cluster, you have back pressure capabilities. So if you are receiving a lot of data at one time, you can slow down and read less data from the inputs to protect your applications. You can also scale up horizontally or vertically your application to be able to handle all this load. And as you can see, it's mainly configuration driven. There is no development. Of course, you can do some development if you need to create a new processor, but usually you don't have to do it because you already have the connector for your systems. So why NiFi? Why NiFi for this use case? First, because we have a large set of connectors out of the box. So we can connect to brokers, we can connect to things that you can find in the plants like CoAP, MQTT, or OPC-UA. Some systems have also like traditional database. We can connect to JDBC, to FTP servers, and so on. And all of this can be done very easily, so we don't need experts on each plant, which is a real problem, because usually the OT people don't have the same skills as someone working in the IT or in the bank or this kind of stuff. Then we have also a small version of this platform, which is NiFi. It's especially C++ or Java agent that's really lightweight in terms of consumption of CPU and RAM that can be deployed on the edge to be like the first agent in place to take this data and push it into NiFi. So we can have this nice multi-level architecture. Then we can, at the edge, do also some processing. So we can like filter the data that we don't need. Like we will see in the demo, if the value of sensor is greater than 500, we know that this value doesn't make sense, so we can drop it and don't transport it into the data center to reduce our bandwidth usage, which can be very expensive for satellite and this thing. We have also command and control tools to be able to monitor and control everything from central position. So let's say you have 1,000 agents deployed in the wide. You can, from one central point, say, okay, this application is running, it doesn't do any filtering. I want now to deploy new application that filters some events. I can do it from central point. And finally, we have this hub and spoke architecture. Actually, in NiFi, there is something called site-to-site, which is an internal protocol that helps different NiFi clusters communicate between them and can be also used by this agent. So you can have really distributed architecture with different deployments, some on-prem, some on cloud, on the edge, and they can exchange information back and forth between them. So it makes the integration really easy. Of course, you can use also some REST API calls or MQTT as a way of communicating between them, but this is something, an option that comes with the tool itself. And finally, something really important when you start working on these critical systems is the end-to-end lineage and security, which is built in NiFi directly. So the other challenge is we can tackle it with Apache Flink. Almost of you here now watch Apache Flink, so I will not introduce it like NiFi. But here, when you are working on IoT, the information that you are receiving from the plants can arrive late, so event time is very important here because there can be like small or very large delay. Some plants can be disconnected from time to time, so it's really important to have these nice features of Flink to be able to manage this situation. Light arrival is also another topic that's important, so we can do our aggregation, we can decide how we will react and adapt our production plan, but we need also to be able to capture events that arrive after, because maybe one plant or maybe one IoT edge was disconnected, and upgrade and update our application. Then we have the state management. So when you are working on the systems, they have different relations between them, and we need to keep the state of this object that are in real time and in real life and see what's happening to be updated currently with when we're receiving our events. And finally, industrial IoT is one of the biggest source of data today. So we need something that can scale at very large to do also some aggregation, some complex event processing at the scale, which Apache Flink can do. So it's really fits in our needs in terms of processing. So now we have MinIFI and NiFi bringing the data, and we have Flink processing it. What we need between the two. So there is, if you look to Apache Flink documentation today, we have a NiFi connector in Apache Flink, which is mainly based on side-to-side protocol that I described before. So there is direct link between the two, which is nice because you don't need another distributed system between the two. You don't need to manage it, to configure it, monitor it, and so on. However, if you have like your Flink application is down because you need to upgrade or because there is an issue or a bug, the data will be stored temporarily in NiFi, but NiFi is not data store. It's not a broker. It's here just for moving the data. We have internal queue, so we can keep the data for some time, but we are supposed to delete it when it's delivered to destination. So you can, if you have like long time down from the application side, you can be in trouble. So the other pattern is to have Kafka between the two, which is real broker. It can be like keep your data retention between the two. So if you have any problem from one side or the another, you can scale it and you can keep more data. And of course, if this data is required or used by other application, they can consume it. They can subscribe to different topics. If you have like several pipelines where you are reading from one topic, writing to another one, Kafka is also a good fit here. So usually we'll end up with the second option, even if we have like this direct integration between NiFi and Flink. So the architecture looks like this. If we look to the different plants, we need to be able to connect to internal data sources, bring the data into our data center or the cloud. So usually you already have like some stuff that are running inside your plane. There is several actors present, like PTC, ThinkWorks, and so on, or maybe some open source solution like PLC4X, and they are using some standard to communicate. MinIFI can get into the machine, can get into the sensors, but usually there is already something there, so we don't have the possibility to go and replace them. So what we do usually is we are at the gateway level where MinIFI will collect the data that are connected by this different solution and then send it into our data center to NiFi. NiFi will receive the data stored in Kafka. We'll also do the enrichment with the different maintenance ERP data that will need to have the context of what's happening inside my production. And then we'll start doing the transformation with Flink and the ETL part and also the CEP part. Some of the data can be stored for like long storage on S3, on HDFS to enable all the machine learning feedback loop, where we can decide what are the most important variables for us to monitor, and we will integrate this feedback into our real-time application in Flink. So in terms of workflow, it looks like this. We have my MinIFI agent deployed in different plants. They will be sending data directly into NiFi. I can do some ETL, like transform the JSON into Avro before sending it, pushing it to Kafka. But we need also some other sources. So this is an opportunity for us to bring like any ERP, CSM, or maintenance systems data into our architecture. And then we will have mainly two destinations. The first one is we can store it on long-term storage. And for real-time processing, we'll push it to Kafka in, let's say, IoT and some other topics. Then this is the work of Flink for doing the processing, so we can do it for ETL. So one of the challenges is here, we are receiving data from different time word or beginnings, and event time is really important. So before being able to do any kind of processing, we need to bring all these events into the same time and merge between them. Then we can start doing the analytics, which can be doing some aggregation, filtering, and comparing to different threshold. Then we'll have our Spark and machine learning that can be used to reduce the complexity. And I will pass it to Jan to talk on this.
Thanks. So, as Abdel is getting ready and bringing up the demo, just in preparation of what you're going to see, imagine you have this manufacturing pipeline, just a schematic view. We have different sensors. I mean, this is pretty normal. We suspect that errors that we look at in the end of the manufacturing process are somehow related to rotation of the device, or the speed of the rotation during the manufacturing process, and vibration. We think that it's probably temperature and pressure is not related to that, and then at the end we have visual inspection, and we pretty much say, okay, we're worried about the size and the dimensions of the item, right? So if it comes out as too large, it's no good. Yeah, and so we have some thresholds around this. What we want to do, we want to be able to say, under these conditions of these sensors beforehand in the manufacturing process, when they are like this, we can predict that this thing at the end is already, we already know it's not going to be a good item, right? And that's what we want to do. We want to find out the relevant features, the relevant settings that play into bad quality at the end, and the ones that we need to watch the most. So first of all, we want to show you how we set up the whole data collection thing, the substrate that we need, that Abdel was talking about, in order to do this real-time analytics with Flink, but then also machine learning and deploying those this knowledge and the model back into the pipeline.
So for the demo, we are using Cloudera cluster, which is data platform with different tools. As you can see, we have Flink here deployed, we have NiFi here, and we have Kafka as well. So if we look, for instance, here on Yarn, we can see that we have our Apache Flink application running, which is doing some processing. So mainly reading from one Kafka topic, doing some aggregation, and then sending back to another Kafka topic. But what's happening? Let's step back and see how we were able to get the data. So if I look to one of my plants, I have like one MQTT client here. As you can see, we are, in each plant, we have an MQTT broker that are receiving sensor data coming from the plant. We have some timestamp, and we have different sensors. So the idea is to be able to bring all this data into my cluster. So what we need to do first is use the CEM, which is the edge management part. So here we have an application that I designed here, but will be deployed on all agents that are in the plant. So what I'm doing here mainly is, let's say, I need to consume data from MQTT. So here everything is happening through UI. I'm configuring my endpoint, my broker, information, topic, and so on. Once I have this data, let's say, I can detect which sensor data has errors. So I need to drop them before sending them. So here, for instance, since my data is JSON, I'm able to extract some information directly from this and put them as metadata, which is sensor 0 and sensor 1. And based on this, I will be able to do some filtering. So for instance, I can say, if I have sensor 0 or sensor 1 is greater than 500, for me, it doesn't make sense to get this information because I know it doesn't make any sense. And then send it to NiFi here through site-to-site communication. Then we are in the data center or in the cloud. We are receiving this information from the plant through this input port, as you can see, and we are in the NiFi realm here. So what's NiFi? Actually, you have like set of processors, the connectors I was talking about, and you're designing your flow like this. Let's say you have, you need to get some data from FTP, so you can look for FTP, and you have some processors, get FTP, and then you can click on it, and you can configure it all the parameters. And then you will connect it to another processors, and you are working and bringing your flow like this. So for the demo, we have already prepared workflow here. So let me just stop this one, and to be able to delete this. And as you can see, data is received in real time here. So you have this queue in which we have all the events that have been produced in our tree plants and we are receiving in real time. So when I look inside them, I can see the content which is the same as the sensor that you saw. Okay? So what I want to do with this data is first do some lightweight ETL. So first we have a schema designed for this event. So we have defined it in our schema registry. We are using it here. So we are just saying that, look, all the events that are coming from here should be parsed, serialized with a sensor cleaned. And then let's say we have some particular transformation that we need for plant 2, we can do filtering. So here, for instance, we can say if plant equal 2, I will have 2 relationship and I will do different processing. Now, once I have my data, first thing to do is try to change the format and of this event. So as you saw, it was like sensor 0, sensor 1, and sensor 2. So I need to do some mapping between this sensor and what they represent. So I'm saying here that plant ID will be always plant ID, but for instance, sensor 2 is my speed, sensor 2 is my vibration, and so on. And you can notice here we are using SQL. So we have also support of SQL. We can receive events in real time and work on them on SQL. So for instance, I can say if sensor 0 is greater than 50, so for me it's error. Otherwise, error will be true. Otherwise, it will be false. And then all this data is going to Kafka into the IoT topic. So let's see what's happening now in Kafka. Through SMM, we have this UI where you can see the 4 components of your Kafka ecosystem, the producers, the consumers, and the different topics and their partitions. So we are producing in IoT here. I can go and see the events directly from Kafka, so you can see the timestamp, the plant ID 1 is healthy, and so on, all the information that we are collecting. If I click here, you can see who is producing or consuming from each topic. So for us, it's IoT. So as you can see, NiFi is producing here, and we have our Flink processor, which is our Flink application, reading from this. So I can select here and filter on IoT because I want to focus on this use case. Flink processor is doing some processing and then writing back into this IoT error. So when we look inside it, we have this counts through windows, and we are mainly counting for each plant how many errors we have seen to start our treatment. And we can also have some information like here, how much my Flink application is lagging behind the data production, so maybe I need to increase the parallelism. We can also go inside the topic to have more information, for instance, on the latency and so on. So you can see when we started the simulation, when we stopped it, and so on. So now the data is in Kafka. I will let Jan talk on the different steps.
Thanks. And really, all of this, the wrangling part in front of this is a part that, as I'm sure as you all know, is the most time-consuming part. And even though we're spending quite a bit of time to introduce the concepts here, this is what's supposed to make this much, much easier and less time-consuming so that you can actually focus on the processing part. As Abda was showing, we have our IoT processor running here that is just consuming from Kafka and putting things back into Kafka. And what we basically want, this is a very simplistic example, of course, this is basically just working on a window, and we want to count the frequency of errors in that window. And what you ultimately want to do if you monitor the quality here, you can think about different manufacturing plants, different manufacturing lines, and then you do sort of cross syndication, where you say, okay, now I see a spike of an error, and every time that happens, the dashboard's supposed to go to red. And when that happens, you know that you have a quality problem. But as you go into the cycle and you see more red lights flashing, you also want to make sure that you now potentially don't only have red lights, you want to have yellow lights. You want to be able to predict what's going on. If you want to do this, you saw as well that we are also putting this stuff into Kudu, and after the errors get generated, finally in the Kafka topic, we are also putting them into Kudu. So we have Kudu is a relational data store that we have, And this is, for example, this is a histogram that we're building from our Hue UI on this Kudu table, and you can see how the events are popping up. Each of the bars represents one of those 15 seconds window that Flume was creating, and then we think about putting a threshold in at 10, but that doesn't happen currently. Currently, it's actually going pretty well. So this would, in the real world, this could be an example that the customer could live with in terms of quality yield. Then we also actually, though, collect all of the raw errors, and that allows us to do some deeper analysis. And as you can see here, this is basically a quite simplistic linear logistics regression model that is taking some of the features that we have in there. And runs a logistic regression, which means it comes out, I predict this part is going to be an error or not. If we run this, we can see if we correlate the different features with each other up here, that, for example, the speed and the vibration, they are very strongly correlated, right? So these other ones, the noise, the temperature, the batch size, they've got almost nothing to do with the error. And this is our leading variable, the size, right? So every time the size goes bad, this correlation means, these two numbers means the speed and the vibration kind of also go bad. And this is a classic case for doing a regression model. So now we are running this. We are trying 3 different algorithms for the model. We can actually see here, if we do a simple logistics regression, we get a 96% score. That means with those features that we have selected here, which is a bunch of them, we have a pretty high precision for this model. So without actually knowing, was this an error or not, just based on the sensor readings prior in the manufacturing pipeline, now we pretty much know, okay, we can predict this with a very high likelihood that this part is going to be an error. So if we want to, if we get these readings, then we can actually stop, right? We don't want to produce 1,000 different cars. In the meantime, we're going to stop now. We're going to recalibrate those sensors, and we're going to recalibrate the manufacturing process so that the end result is going to be better, because we don't want to waste a lot of money and a lot of material to produce defective parts. When you change the different features, so when we, for example, drop more features, which can be good or bad, it always depends on how the model performs, but if we do that, you will see the precision of the model also changing, and that is basically playing with feature selection. You can now see that here for the SGD classifier, the performance dropped significantly, only an 83% chance to get it right. So here we cannot predict so well. So it's actually better to keep more of the features. But the key point of this is that the next evolution of Flink at our distribution will be to put these models, these predictors, into the operators in order to not only detect errors, but also to predict them. And you can do this today. You can just code this up. But what we do with this tool that you just saw with Cloudera Data Science Workbench, we are running everything in Docker containers. And this is much more about making these models operational and running them directly side by side in a Flink operator. So this is basically the roadmap material, and I think that's it, right?
Yeah, so we still have like just one slide, because one can ask the question, what this kind of architecture is bringing compared to existing solution in the manufacturing. So just to sum up, here we are trying to have cross-plant and enterprise analytics, where existing solutions are already in the plant and trying to do some analysis in the plant itself. And we can miss some important information. So for instance, one of our customers, they have like isolated teams in each plant, and they think that the yield and the productivity of their process are good. But when you compare with other plants using the same materials, the same process, we can see much important difference. So it's an opportunity to detect this situation and change them. In terms of data ingest, we are here focused on the IoT part, but also the enterprise, to build this 360 view, if we can say it. And then we have the storage and the processing, which can be batch or real time, depending on the use case. So for us and for this community, you already know Apache Flink, Apache Kafka, you know that it works together. So here we are also bringing NiFi to bring the data until Flink and Kafka. And for one last slide, we are hiring Flink and Kafka product manager. So if you are a product manager and want to work on this stuff, you are welcome to discuss with us. Thank you.